Alrighty, folks, we are back. Thank you for tuning in. You are listening to a mathematician's favorite music, Logarithm and Blues. Anywho, continuing with logarithms, we're going to look at their properties now and start doing some real problems with them. Get into their properties, get into how to work with them, and that'll lead us into being able to do some application problems in the near future. All right, so back to the definition of a logarithm again. We talked about this previously, but reviewing. For a base that's positive and not equal to 1, you have the exponential equation a to the y equals x is equivalent to y equals log base a of x. We had gotten this when we were looking at the inverse of an exponential function. Exponential function, you have f of x equals a to the x, or y equals a to the x, and you want to find its inverse. You swap your x and y. You have a to the y equals x, and that's equivalent to y equals log base a of x. So log base a of x is an exponent. Logarithm is an exponent. Your a is your base of the logarithm. Your x is your argument of your logarithm. And that argument is always positive. Okay, so in knowing that definition, you'll be able to, excuse me, you'll be able to work with some logarithms and being able to kind of manipulate them back and forth. Um, Let me get my little pointer going here. So let's say you have something like 2 to the 5th equals 32. Okay, so this is like having the form a to the y equals x. Well, you can rewrite that in logarithm form. You can say log base 2 of 32 equals 5. So these two are equivalent. 2 to the 5th is 32. If you multiply out 2 5 times, you get 32. But you can also write it in logarithm form by saying log this base of 2 from the exponential equation is the same as the base 2 in the logarithmic equation. The log is an exponent, so this exponent 5 is what the log equals. And then this 32 here is the argument of the logarithm. Or if you go the other direction, like let's say you have log base 4 of 1 over 64 equals -3, and they want you to rewrite that in an exponential form. You can take the base of 4, raise it to what that equals, the exponent, and then say that that equals the argument of 1 over 64. And just think about that for a second. We know 4 to the -3 is 1 over 4 cubed, which is 1 over 64. So we've stated truth here. But that's how you go back and forth between exponential and log, or log and exponential. Okay. Now, knowing that definition, we can also work with equations that have logarithms in them. A log equation can be solved by converting it to a type 1 exponential equation, which you did some solving of in a previous lesson. Solve using those learned methods you've already been doing. You must check your solution in the original equation. Again, use the fact that your a is positive and not 1, and that a to the y equals x is equivalent to y equals log base a of x. Okay, and before we do, just real quickly, some special types of logs. If you just see log of x and you don't see a base, then it's a common logarithm, and the base is understood to be a 10. If you see ln of x, that stands for natural log. It's the same thing as log base e of x. Remember that e is an irrational number that you'll see commonly in like compounded continuous interest or something. So just wanted to make you aware that those two, that's what those two are if you see them. All right, so let's solve a couple of equations. Let's say we have something like log base 3 of 81 equals x. Well, in the log form right now, we have not learned a technique to handle log base 3 of 81. Right now, if you try to put it in your calculator, you're probably going to find you're going to struggle a little bit because the log key on your calculator is a common log or log base 10, but this question has log base 3. But we've got some techniques under our belts now. We can rewrite this log equation as an exponential equation. Base of 3, it equals x, it equals the exponent, argument 81 is what this equals. And then this is a type 1 exponential equation. You can work on rewriting both sides so that you have the same base. If you have 3 to the x over here, then you need 3 to something over there. Let's see, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. So that would be 3 to the 4th. If you have the same base, then the exponents must be equal to each other. So log base 3 of 81 equals 4. Yay. So that's one example. Let's see here. What else do we have? Let's say we have something like log base 3 of x minus 1 equals 2. Okay, let's put it into exponential form. 3 squared equals x minus 1. Oh, this one's not so bad. 3 squared is 9. Just a simple linear equation. X equals 10. That wasn't too bad. So 10 minus 1 is 9. So log base 3 of 9 equals 2. Makes sense. 3 squared is 9. So that works. All right. Let's say you have something like log base x of 5 squared equals 6. Let's see here. So we could rewrite this as x to the 6th power equals 5 squared. Okay, now since the x is in the base and 5's over here in this base, my best bet will be to rewrite this so that the exponents are the same. If their exponents are the same and they're equal, then the bases must be equal. Well, 5 squared, I really can't break that down anymore. 5 squared, yeah, I'm going to leave that there. But x to the 6th, I can rewrite that as something squared. If I write this as x cubed squared, I'm in business. Because 3 times 2 is 6. And now they both have the same exponent. Now they're both squared. So that tells me that x cubed must be 5. So x must be the cube root of 5. Or you could, if you don't like saying cube root of 5, you could say x is 5 to the 1/3. All right, so you have 5 to the 1/3 raised to the 6th power. That would be 5 squared, and that equals the argument 5 squared. Yay! Okay, so that worked out. Sometimes you have to use a little creativity and thinking. So either get your bases the same and set the exponents equal, or get your exponents the same and set the bases equal, all depending on where your variable is located. Well, let's do one more of these. This one looks like fun. Log base 1/4 of 16 squared over 2 to the negative 3 equals x. Yeek. Oh boy. So I've got 1/4 to the x power equals 16 squared over 2 to the negative 3. Now since the x is in the exponent probably my best bet is to get the bases the same and then set the exponents equal. So what do I got here? I've got a 1/4. On this side I have a 16 squared and a 2 to the negative 3. Let me move that 2 to the negative 3 up and make it 2 cubed. And let's see, 16 can be written as 2 to a power, can't it? Because 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So 16 is the same thing as 2 to the 4th. And 4 times 2 is 8, so 2 to the 8th here. 2 cubed times 2 to the 8th is 2 to the 11th. I'm not going to multiply all that out and get this huge number right now, because I really want the bases to look the same on both sides, and then I can set the exponents equal. So what I'm going to do instead is concentrate on how I can get 1/4 rewritten as 2 to some power. Well, 1/4 is the same thing as 4 to the negative 1, so far I've got 4 to the negative x. But 4 can be written as 2 squared, so I end up with 2 to the negative 2x. Excellent! Now the two bases are the same, so negative 2x equals 11, so x equals negative 11 halves. Awesome! There we go. All of that work. But, you know, I bet if you put in your calculator right now, you could take 1/4, raise it to negative 11 halves power, and then take 16 squared divided by 2 to the negative 3, and you should end up with the same thing. I accidentally made a mark there. Better erase that because I don't want that to be on there. All right, so there's a little bit about exponential equations and logarithmic equations into exponential equations. Next, a little bit about properties of logs. Remember, logarithms are really exponents. So a lot of these properties come from the thinking about exponential rules. Like you got log base a of 1 equals 0. We're assuming a is positive, a is not 1, and any k's are real numbers. Well, if you write this in exponential form, a to the 0 equals 1, we know that. That's an exponent rule. Makes sense. But you know, if you have a question like log base 4 of 1 equals what, then you know the answer. You know it has to equal 0. Right? Number 2, log base a of a to the k equals k. Well, if you write it in exponential form, a to the k equals a to the k. That makes sense. But then if you have something like log base 4 of 4 to the 17, and you're trying to see what that equals, well, log base 4 of 4 to the 17 is going to equal 17. And here, a raised to the log base a of k equals k. If you rewrote it in logarithmic form, log base a of k equals log base a of k. Like, oh, okay. As long as k is greater than 0, which has to be here because k is the argument in the log. But if you're doing a problem where you're given like 4 raised to the log base 4 of 9, and you're trying to see what that equals, well, based on this property, you can immediately say, oh, I know that that's supposed to be 9. So there we go. So properties can help you work on some problems pretty quickly. And then some other properties. Well, if you're multiplying two expressions that have exponents, as long as you have the same base, keep the base and add the exponents. Well, log of a multiplication equals the sum of logs. Log of a division equals a difference of logs, because it's like you're subtracting your exponents. Also, power to a power, you multiply exponents. Well, down here, log base a of x to the r, That's like having an exponent raised to the r power. You multiply them together. You multiply the r with the exponent, log base a of x. Okay, but how can these properties help you? Well, you're gonna have some problems where you have to like write things in different forms. Let's say you have something like log base 3 of 4p over q. And you really need to rewrite this. Well, using property number 5, you know that you can rewrite this as log base 3 of 4p minus log base 3 of q. And also knowing property number 4, you know you can take this log base 3 of 4p and rewrite that as log base 3 of 4 plus log base 3 of p, and then you still have that minus log base 3 of q. So there's that one. Now be careful though, because if you have something like log base 6 of 7m plus 3q, well, you can't rewrite that. Because the properties say log of a product equals the sum of logs, log of a quotient equals a difference of logs. It does not say anything about log of a sum or log of a difference. You know, there's a difference here. This log 6 of 7m plus 3q is not the same thing as log 6 of 7m plus log 6 of 3q. Those are two different things. And then again, if you have an exponent in your argument, the exponent can come out front and multiply with your log. So let's say you have something like log base z of x to the 5th y cubed over 3. All right, well, first of all, you know that from property number 5, you can break this up as log base z of x to the 5th y cubed minus log base z of 3. And then by property number 4, you can break up this into log base z of x to the 5th plus log base z of y cubed. You got minus log base z of 3. Then by number 6, log base z of x to the 5th, you can bring the 5 out front. 5 times log base z of x. Then for the y cubed, you can bring the 3 out front. Log base z of y minus log base z of 3. So if your argument, the entire argument has an exponent, the exponent can come out front. Multiply with that log. Being able to rewrite your logs can be helpful with certain equations and other problems down the road. Now you have to be able to go both ways too. You know, don't have to just take a single log and break it up. You also have to be able to take something that's broken up and put it in, combine it into a single logarithm. Let's say you have something like log base a of x plus log base a of y minus log base a of m. So using your properties, you can combine all this into one logarithm. Log base a of x plus log base a of y, that's a sum of logs. You can rewrite it as the log of a product, log base a of xy. And then you have a difference of logs, and you can rewrite that as the log of a quotient, like that. So that's an example of writing a big logarithmic expression into one log. Another example, we got 2 log base m of a minus 3 log base m of b squared. Well, first, I need the 2 here and the 3 here out of the way. So I can use the exponent rule, exponent property, and rewrite this as log base m of a squared minus log base m of b squared cubed. So I've got log base m of a squared minus log base m of b to the 6th. And then that difference, I can rewrite that as a single logarithm, log base m of a squared over b to the 6th. Just like that. So know those properties of logs, definitely practice going back and forth from longer logarithmic expressions into single logs, or from single logs back into longer expressions. Okay, and then one more thing. You don't always have logs in the bases you need. Something called the change of base rule. If you're interested in seeing how this is derived, you can check it out. You can check out a proof in your book on page 365 as to how the change of base formula comes about. But this can be helpful when you're punching stuff into your calculators. Your calculators having those common log or natural log buttons. But you might have a problem where you have like log base 3 or log base something else, you know. So you need to be able to punch it in. As long as your as long as your bases and your arguments are all positive, and as long as your bases are not 1, then this is called the change of base formula. Any log base a of x can be rewritten as the log of some other base b of x over the log of some other base b of a. And that gives you a convenient way of working with it. So for example, let's say you have to find log base 9 of 12. Well, your calculator may not have an option to do log base 9 of 12. Some of the more advanced, newer TI-84s might have that option, but not all of them do. My old TI-83 doesn't. So, according to the change of base formula, I can use common log, log base 10 of the 12, divided by common log, or log base 10 of 9, and I can figure out what that equals. Or, if I don't like that one, I can use natural log of 12 over natural log of 9. It really doesn't matter what base you use here, as long as you use the same base on the top as you do on the bottom. But I'm going to use common log or natural log because that's what I can use in my calculator. Right, so let me pull up my calculator. So let's say I do common log, log of 12. I have the log button right here. Log 12, close parentheses, divided by log, so I have that log button right here, of 9, enter. And there it is. That's what it's equal to. It's a decimal number, 1.130929754. But you know, it doesn't matter what base you use. You're using the change of base formula. So you could, instead of saying common log, you could say natural log of 12 divided by natural log of 9. And you get the same answer. That is what the log base 9 of 12 equals 1.130929754. So there you go. All right, so yeah, if you hadn't noticed it before, even your scientific calculator should have a log button or a log on a menu or on above a button somewhere, and also should have LN for natural log. Graphing calculators, you see them over here on the left side, but different calculators have in different spots. And of course, as always, if you're trying to use your calculator and you're having trouble, please don't hesitate to contact me. I'll try to help you work through it and figure out how to make it work. Just tell me what kind of calculator you have, and then we can do a little poking around online or whatever and try to figure out how to make it work. Okay, so there you go. So there's your logarithms, properties, how to do some problems in it. Have fun, practice, practice. And we will continue some more of this with some word problems next time we meet, or with some more equations and inequalities, excuse me. And then later another lesson with some applications or word problems. All right, so there you go. Have a good day.